All right. So, like I said, this stuff that we're moving into, which will take us through February, and then it'll really kind of take us up to spring break. We're going to do our test over this right before spring break. In this stuff, I get excited about because I love algebra stuff. I love working with numbers. This is stuff that, depending on your level that you end up teaching at, you may actually be teaching. And just keep an open mind for your future, because most of my coworkers are not in the age group that they thought they were going to teach in when they started. I'm not even in the age group. I never thought I would teach middle school. I said I will only teach high school and above, but I ended up falling in love with middle schoolers. I have another coworker who said she will never teach above like 4th, maybe 5th grade, and she only teaches middle school. So keep an open mind. You might not end up where you thought you would, but this stuff will be important regardless. For most of this stuff, we're not going to use a calculator. While I know you are capable of typing into calculators, I also need to know you're capable of teaching this to students without a calculator. So this we actually talked about a little bit before our last test, definition of prime and composite numbers. So we said that a prime number is a natural number that's greater than 1, that has exactly 2 factors, or you could call them divisors, itself and 1. So it can only be divided by itself and 1. Composite number means it's going to have more than 2 factors. Notice that 1 is not considered prime or composite. By definition, both of those have to be greater than 1. So we're just going to list the 10 smallest prime numbers, the 10 smallest composite numbers. Anyone want to get us started on prime?
1.
We can't do 1. 2. 3. 5. Good. 7. What about 9? Nice. 11. 13. 17. 'What'd you say? 19. 23. 1, 2, 3, 4, 5, 6, 7, 8, 9. One more.
7.
What can 27 be divided by? 9 and 3. 29. Okay. Composite numbers should be easier because it's definitely all the even numbers and then some of the odds we skipped. So 4, 6, 8, and 9, 10, 12, 14, and 15, 16, 18, I don't even know how many that is. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oh, 10, perfect. Questions on prime versus composite. That is a concept that we start teaching in elementary school. All right, so after that, we just have a little more practice. So I'm actually going to, I'm going to skip ahead for a second. Look at this chart with me. So these are divisibility rules. These are not by any means all of the divisibility rules, but these are the most common divisibility rules that you can use when determining if a number can be divided by one of these. Some of them are pretty obvious, and you probably already use often. So to determine if a number can be divided by 2, we look if it ends with an even number. So 0, 2, 4, 6, or 8. If that's the last digit, it can be divided by 2. The other ones that you're probably extra familiar with would be 5. If a number ends with a 0 or a 5, it can be divided by 5. And then 10, if the number's last digit is 0, it can be divided by 10. Those three you're probably very familiar with. Some of the other ones, however, are quite helpful if you can learn them and get them memorized. So both 3 and 9 have the same idea to them. It's just a different number. So for 3 and 9, what you're going to do is you're going to add up all of the digits of the number. So if you look at 531 is the example. 5 plus 3 is 8 plus 1 is 9. If after you add them up, if that sum can be divided by 3, the whole number can be divided by 3. Or if that sum can be divided by 9, the whole number can be divided by 9. So because this sum is 9, that means I could divide 531 by 3, or I could divide it by 9. If we look at the 9 example, it's a much bigger number, 621,513. If you add up, 6 plus 2 is 8, plus 1 is 9, plus 5 is 14, 15, and then 3, so you get a sum of 18. That can be divided by 3, that can be divided by 9, so you could divide that large number by either of those. It comes in handy, but it only works for 3 and 9. So I think it was last semester when I taught it, I wasn't clear about that, so then students were like adding up the digits and dividing it by 7 or things like that. This strategy only works for 3 and 9. 6 is a nice one because 6 says if a number is divisible by 2 and by 3, it's also divisible by 6. So if you do the test for 2 and 3 and they both work, then 6 is always a great one. 4 and 8 are fine. They work better for with larger numbers. So 4 says if you look at just the last 2 digits, so in a number like 1,924, 24 is divisible by 4, so the whole number can be. And with 8, it's the last 3 digits. So like if 168 can be divisible by 8, divided by 8, then the whole number can. It still requires you to do a little work. It's not as straightforward, but they can be helpful with some larger numbers. And then the 11 one is interesting as well. So what the 11 divisibility rule says is that you start with the first digit and you add every other digit, and you keep that sum, and then you add the opposite alternating digits, and you keep that sum, and you subtract the two sums. And if the difference is divisible by 11, then the whole number is. That would also mean if the difference is divisible, let me say this differently. If the difference is 0, 0 technically is divisible by 11, so that would be divisible by 11. So for instance, like the number 121 or 132, we know those numbers can be divided by 11. So if you take this rule, I would start with 1 and add every other. So 1 plus 1 is 2. And then my other number is just 2. I would find the difference between these two, which is 0. That means I can divide by 11. Same with this one. If I do 1 plus 2, I get 3. Whoops. And then my other number is 3. Difference is 0, so it can be divided by 11. With the example in here, it's a much larger number, 4,807. You would do 4 plus 0 and get 4. 8 plus 7 and get 15. When you subtract those two, you get 11, which is divisible by 11. So can be a little tricky to work through, but if you can get that, that's pretty helpful as well. So keep this in mind as we come back to determining if these numbers are prime or composite. So let's look at 41, and let's just talk through some of our divisibility rules. So can it be divided by 2? No, because it doesn't end in an even. What about 3? Our test is add the digits. So 4 plus 1 is 5. Can't be divided by 3. Can it be divided by 5? No, doesn't end in 5 or 0. 10? No. So then with a number this small, you're really just checking like, okay, could it be divided by 7 or, 11, but we know that's not the case. So this one would be what? Prime. Yeah, someone said that, right? I'd like to believe that. Okay, 51, let's check this. Can it be divided by 2? No. Let's add up the digits. 5 plus 1, 6. Okay, so what does that imply? It can be divisible by what? Or divided by 3. So what would that make this number? Composite. So this can be divided by 3, which implies this is a composite number. Okay, 119. Can it be divided by 2? No, let's check 3. So 1 plus 1 is 2 plus 9, 11. No. Can it be divided by 5 or 10? No. Remember the rule for 4 is to look at just the last 2. So 19, is that divisible by 4? No. We could do the 11 check. So 1 plus 9 is 10. We subtract 1. That's not going to be divisible by 11. So again, really you're checking 7 and maybe 8 if it can be divided by those. So you might have to do a little work by hand, but this one would be prime. Okay, let's check 57. Can it be divided by 2? Nope, so check 3. 5 plus 7. What is 5 plus 7? 12. Can that be divided by 3? Yep. So what would that make this number? Composite. Does that make sense how we're doing that? Okay. Okay, go back to our first unit and think about sets, intersections, and unions with me for a second. Let P be the set of prime numbers and C the set of composite numbers. What would the intersection of P and C be? In other words, what's in both? Nothing. How do we write that? The null set or the empty set. Either one. Okay. What about the union of P and C? And we're going to use our set builder notation. So we're going to say X such that. What would our union be? Everything except one. Okay, so what set of numbers is it a part of? X is an element of what set? The natural numbers, because we aren't including 0, that would be whole numbers, and X is greater than 1. You with me there? Just wanted to throw it back to chapter 1 there. Okay. So we talked about our divisibility tests. So then let's go ahead and just practice dividing some numbers, figuring out what they're divisible by. So first number. We are going to determine whether 16,278 is divisible by these numbers here. Okay, so is it divisible by 2, and how do we know? Good. So it ends in 8. That's an even number, so it is divisible. And notice in this type of problem, I'm not necessarily asking you to divide it. I'm asking you to tell me, can you divide it to get a whole number? All right, what about 3? Let's do the test. 1 plus 6. plus 2 plus 7 plus 8. Is that divisible by 3? Yes, so it is divisible by 3. All right, let's look at 5. Is it divisible by 5? How do we know? Good. Doesn't end in 0 or 5. So it's not divisible. Okay, so here's our 8 rule, right? 8 rule says look at the last 3 digits, 278. Now, I don't know about you, but like I wouldn't look at 278 and just know if it could be divided by 8 or not. So like I'm going to do that work. So 8 goes into 27 how many times? 3 times. That would give us 24. When we subtract, we get a remainder of 3 and we bring down an 8. Does 8 go into 38 evenly? No. We would say it goes in 4 times. That would be 32. And instead of a remainder of 0, I'm getting a remainder of 6, which would then put me into a decimal. So I would say not divisible. All right, and then our test for 11, so we're going to start at the front and we're going to take every other number and add it. So we're going to do 1 plus 2 plus 8. That equals 11. And then we're going to take the other numbers and add them. So we're going to do 6 plus 7. That equals 13. If I take the difference of these two numbers, the difference is 2. Is that divisible by 11? No. So this is not divisible. Okay, why don't we take like 3 minutes, 4 minutes? With the person next to you, or you can do it by yourself, check with the person next to you. Try this next one on your own, and then I'll put the answers up on the screen and see if you get them right. Okay, go ahead and check your answers when you're done. See if you got them right. If you did not, let me know if you have questions. All right, let's move on to prime factorization. I find prime factorization fun. But some people don't. But it's fine. It's we make a tree, a factorization tree. I think it's exciting. So here's the thing. Prime factorization is taking a number and it is writing it as a multiplication problem. So writing it as a product. But you can only use prime numbers in the product. So our list of prime numbers of 2, 3, 7, okay. Oh, I forgot 5. 2, 3, 5, 7. Okay, that list of prime numbers is what we want to end up with in our answers. And then it's important that you note that when you write your answer, it should be in ascending order. So we go from smallest prime number to largest. And it has to use exponents, meaning if there's multiple 2s or multiple 3s, we write it as an exponent rather than writing the 2 or 3 out every time. So this is what we're going to do when we want to find the prime factorization. We're going to take our number and we are going to come up with 2 factors that would multiply to 84. It can be any 2 factors. You can choose to start with a prime number or you can come up with any 2 numbers you can think of. So 84, I need 2 numbers that multiply to 84. Yeah. Love it. 2 and 42. Once you have those 2 numbers, you're going to evaluate each branch of your tree. So is 2 prime? Yes. When you have a prime number, circle it, and then you're done with that branch. But 42 is definitely not prime. two numbers that would multiply to 42. 6 and 7. Are either of those prime? 7 is. Circle 7. 6 is not, so we're going to break it down further. How would we break that down? Yep, 2 and 3, both prime. Okay, so here we go. We're going to write our final answer. We're going to start with the smallest prime number we have, which is 2. We're going to count how many 2's we have, and that becomes the exponent on the 2. So I have 2 2's, so this is 2 squared. Times, we use our multiplication dot because at this point we're moving into solving equations where we have variables, and x is just going to be confusing. Our next one would be 3, and there's only one of them. So you can write 3 to the first power, or you can just leave it 3 times 7. If you are unsure if you got the right answer, you can do 2 squared times 3 times 7, and you should end up with 84. But this would be called the prime factorization. And prime factorization is used in a lot of different applications of math. So when we're talking some of our real world problems, but even when we're looking at, what was I thinking of? I don't know. I lost my train of thought. It'll come back to me eventually. Let's do the next one. 495. I need two numbers that multiply to 495. Nice work. 5 and 99. If you didn't know that, you should do the work to get that, because remember, we're trying not to use calculators. 5 is prime. Is 99 prime? No. What is 99 broken down to? 9 and 11. Good. 9 and 11. Either of those prime? Yes. 11 is prime. Circle it. And then 9 can be broken down into what? 3 times 3. So when we write our final answer, we're going to start with the 3 because that's the smallest. We'll have 3 squared times 5 times 11. All right, let's go on to our next one. 4,004. Anyone want to get us started? Elise. Perfect. 2 and 2002. 2 is prime. Circle it. Anyone want to take our next one for us? You can do it.
2 and 1001.
Excellent. 2 and 1001. Okay. I don't know 1001 off the top of my head, so we're going to go through our divisibility rules. Can it be divided by 2? No. 5 or 10? No. So let's check 3. 1 plus 0 plus 0 plus 1 is 2. No. 4, we look at the last 2 digits. That means 1. 1 can't be divided by 4. 8, we look at the last 3. Also 1. Can't. 9 didn't work because that's the same as 3. So then we're looking at 11. Remember, 11 we do alternating. So 1 plus 0 is 1. 0 plus 1 is 1. 1 minus 1, 0. That can be divided by 11. So we know we're going to have 11 times something, but we're going to have to do that math, figure out what it is. 11 cannot go into 10, but it can go into 100 9 times. That gives us 99. When we subtract and do our borrowing, we end up with a remainder of 1, and we bring down that other 1. 11 goes into 11 one time with our remainder of 0. So 11 times 91 would be 1001. 11 we know is prime. 91 we don't know, so we're going to go through some of our tests. Can it be divided by 2? No. Can it be divided by 3? 9 plus 1, 10. No. 4, we just kind of have to check it. You can't. 5, no. 10, no. 9, no. So then we're looking at 11, no. 7 is really the only one we don't have a really great divisibility test for, and you kind of just have to test it out yourself. Well, I shouldn't say 7's the only one. There are others too, but we're going to do 7 here. 7 goes into 9 once. Remainder of 2, when we bring down that 1, 7 does go into 21 3 times with a remainder of 0. So 7 times 13 is 91. And now those are both prime. So I would say just don't assume, make sure you check the 7. All right, so for our final answer here, we're going to do 2 squared times 7 times 11 times 13. Any questions on prime factorization? All right, solving equations. Does anyone else love solving equations? Okay, there's a couple of you. That's good. So terms you need to know. There's nothing for you to write in this box, just things you need to know, and eventually you'll put on your vocabulary log. So the terms are the addends of an expression. What that means is anything that's separated by addition or subtraction would be a term. So I'll ask you a couple times through here, like how many terms would this be? Terms are separated by addition or subtraction. A constant term is a number with no variable. A variable is a letter or symbol used to represent an unknown value. The coefficient is the number in front of the variable. It's pushed up against it, which means it's being multiplied by it. Like terms are terms that have the same variable to the same degree. So that means like an x and an x squared are not like terms and can't be put together. Because even though they have the same variable, they don't have the same exponent. A degree is the exponent. Equation, expressions that are set equal to each other. A first degree equation, variables only have an exponent of 1. And a solution is the number that makes the equation true. So here are a couple properties of equations that we need to be aware of. And this, honestly, this is what you do every time you solve an equation. This is just like the formal writing of it. Basically, this means if you add something to one side, you have to add the exact same thing to the other side. If you subtract something from one side, you have to do the exact same thing to the other side. Same with multiplication. If you multiply by one side, you have to do it to the other. And if you divide by one side, you have to divide on the other. So let's go ahead and start solving. Our steps, we're going to eliminate the fractions by multiplying by the least common multiple of the denominators. We're going to use distributive property to get rid of parentheses. Combine like terms on each side individually. Use addition and subtraction to rewrite the equation with variables on one side, constants on the other. And then use multiplication and division to isolate the variable. Okay. Can you give me like on a scale of 1 to 5, if you think you're super strong at solving equations, do you think that'd be a 1 or a 5? Make that a 5. And if you think you're absolutely terrible and you have no clue what to do, make that a 1. And then can you hold up a number so I know what we're working with here? Because that'll help me know how quickly to move through this. Okay. Not bad, not bad. Everything's like 3, 4, or 5. So that's good. All right, so remember, the equal sign is like our dividing bar, right? Whatever I do to one side, I have to do to the other side. My goal is to get x by itself on that side. So I'm going to start with any addition or subtraction to get rid of that. So I'm going to start by subtracting 8 from both sides. So we have 2x equals 18. Then, because 2 is being multiplied by the x, I have to do the opposite. So I'm going to divide both sides by 2. And x would equal 9. That would be my final answer. Okay, when we look at example 2, we have like terms. So we have, actually, let me ask you this first. If you ignore the right side and just look at this expression in the box, how many terms? 3 should be your answer. Remember, terms are separated by addition and subtraction. So 3 terms. Because the 5 and the 2 both have an x, and those x's both have an exponent of 1, it looks like they don't have one, but exponent of 1. Those are like terms. When you combine like terms, remember that it is important to include whatever sign is in front of the term. So that minus, that subtraction sign, really is attached to the 2. It's a negative 2x or a minus 2x. So we're combining a 5x and a negative 2x, or we're doing 5x minus 2x. So that would be 3x plus 6 equals 27. What would my next step be? Good. Subtract 6 from both sides. So we have 3x equals 21. What am I going to do after that? Good. Divide by 3 on both sides. So x equals 7. Final answer. Remember, you can always check your work by taking that answer, plugging it back in for all the x's, and then calculating it. And if you get the same number on both sides, you've done it right. Okay, let's go ahead and look at the next one. So anytime we have parentheses, our first step is to get rid of those parentheses using the distributive property. And if you remember the distributive property, it says that anything that's pushed up against the parentheses, that means multiplied, has to get sent through to every part using multiplication. So I'm doing 4 times 3x to get 12x. And I'm doing 4 times a positive 8 to get a positive 32 equals 2x minus 8. Now at this point, we have 2x terms, a 12x and a 2x, and then 2 constant terms. But they are separated by the equal sign. We cannot combine like terms across an equal sign. So you have to move them to the other side first before you can put them together. I always recommend you move the x's first, and you actually have 2 options. You could choose to subtract, I want to write it in a different color. You could choose to subtract 2, oh, that's terrible. You could choose to subtract 2x from both sides like this. What would our other option be? You guys are so smart. Subtract 12x. Okay, which option do you think would be nicer to work with? Subtracting 2x. Kiana, you have a question.
Yeah, why would you do the x's over, like the other?
Like, why do the x first?
Yeah, like, why can't you just move that?
So technically speaking, you can move the other numbers first. As you go further in math, you'll run into situations where you have no solution or you have infinite solutions. And while it is totally possible to see that when you do the numbers first, it's easier to see that if you move the x's first. Because what we typically say for those situations is we say, you know you have a solution if you end up with a variable and a number in your answer. And you know you don't have a solution, or I should say, you know you have no solution if all your variables are gone and you have a statement that's not true, like 3 equals 5. And you know you have infinite solution if all your variables are gone and you have a true statement, like 5 equals 5. You would still get a true statement or an untrue statement. It would say like x equals x, or 2x equals 5x, or something like that. It's just easier to see if it's just numbers. So that's the only reason I suggest it. So we're going to subtract 2x from both sides. So now we have 10x plus 32 equals negative 8. What would our next step be? Good. Subtract 32 from both sides. What would I get on the right? Good. That, I think, is usually the tricky part for students, especially if you haven't done this for a while, for two reasons. One, students see 8 minus 32, and then they want to subtract that and say it's like negative 24, something like that. Also, sometimes students see the two negatives and they remember the multiplication rule. Oh, two negatives make a positive. Remember, that only applies for multiplication division. When we have two negatives that are added, we go more negative. All right, then we're dividing by 10 on both sides. So x equals negative 4. Questions on this? All right, last example, fractions. Some people hate fractions. That's okay. But we have to know how to work with them, especially if you're going to be elementary teachers, because fractions are going to be where you start with elementary, not decimals, right? Like once you teach them natural numbers and whole numbers, you don't jump into decimals, you jump into fractions, because that's the easiest for them to see. I can talk with my 4-year-old about a piece of pizza, and I can say, if I take 2 of the 8 pieces, how many pieces do I have left, right? That's getting his mindset into thinking like, oh, yeah, you have 6 of the 8. Now, he doesn't know yet that's a fraction, but that's where you begin with elementary. So we have to know how to work with fractions. Whenever fractions come into equations, you actually have a couple different options of dealing with it. I like to just get rid of them. So I'm going to talk you through the process of getting rid of the fractions and why it works. But let me know if you have questions along the way. So do you remember a property that says if I multiply this fraction by the denominator, I can cancel those out? Does that look familiar? Say no if it doesn't, or shake your head no. Okay, that is the property that we are going to use to get rid of fractions. And I actually don't want you to write anything yet. I just want you to listen and watch, because how much work you show is really dependent on what makes most sense in your mind, right? So I want to talk through this for a second. What I teach my middle schoolers, because it's what makes the most sense at that stage when you're first learning it, is that you need to get common denominators across the whole thing, right? So I tell them, okay, I want every single one of these to be 12, because 4 and 3 can both become 12 using multiplication. So I say, okay, we know we have to multiply this by 3 and this by 3. So I'm going to have 3 times 3x minus 1 up here. And I'm going to have to multiply these by 4. So I'm going to multiply the tops by 4. And this is going to be 4, and this is going to be 28. Okay? And then what I tell them is I say, oh, okay, great. The denominators are the same. Now we're just going to cross them right out. Now, we don't get into yet the reality of what we're doing. Whoops. Okay, but what we're doing here is we're multiplying this by 12 to cancel, and multiplying this by 12, and multiplying this by 12, because as long as you're multiplying by every part, we can cancel all those 12s out. Are you with me so far? Now, there are some students who that just makes perfect sense to in their minds, and they don't need to go through all that work, because what you can do is you can say, oh, well, I know 4 and 3, I know those can both go into 12, so I'm just going to multiply this whole equation by 12, or 12 over 1, you could write it like that. And I know I'm going to multiply this by every part, and when I multiply this first one by 12, the 4 is going to cancel, and this 12 is going to become a 3. And I'm going to multiply 3 by 3x minus 1. And then I know that when I multiply by this one, the 3 is going to cancel, the 12 is going to become a 4, and I'm going to do 1 times 4. Are you tracking with me? Okay, I'm going to go back and write out finding a common denominator, crossing out the denominator, that. You write what makes sense to you, okay? So our goal is to get all the denominators the same so that we can multiply them all by the same thing and therefore get rid of them. Yes, ma'am.
Is it, since the 1/3 and the 7/3 have the same denominator, is it improper then to start by simplifying and subtracting?
So you absolutely can. Option number 2, you could subtract 1/3 from both sides. So this would leave 3x minus 1 over 4 equals 6/3. And this actually you could reduce to 2 over 1, or just 2, right? At this point, you could multiply by 4 on both sides, and you can solve it that way. All of those ways are perfectly acceptable. This one is nice where the 6 over 3 will reduce to 2. Sometimes it won't. And if you were to get, let's just say something like 5 over 8, and then over here you had 3x minus 1 over 7, and now you're trying to figure that out. There are some people who look at that and they're like, oh, I'm stuck, I can't do anything. So I always go to first get rid of fractions. But if that way makes more sense to you, go for it. And if that's the case, write down what makes sense to you and see if you get the same answer. Because there are multiple different ways to do this, and that's great. You do need to understand them, because if you were teaching them, you would want to be able to say to a student, oh, that way doesn't work. Let's try this way. I have one student who, it's like she can't do normal math. I can ask her, what's 12 minus 8? Can't do it. But if I say, hey, you have $12. Can you give me 8 of them? How many do you have left? Knows the answer in a second, right? You're going to have to find what works with your students, because God made us all different. Their brains are all different, developing at different rates and understanding and processing in different ways. So write the one that makes sense to you so you can solve it and succeed in your class, but understand that there are other options out there. Okay, so I'm going to get them all to 12. And I'm going to multiply the first one by 3. So this is 3 times 3x minus 1. If you're doing this method, it is important that you keep that 3x minus 1 in parentheses, because you're going to have to distribute. So then we have 4 over 12 and 28 over 12. And once the denominators are all the same, we can cross them out, because essentially what we're doing is we're multiplying by 12 all the way across. So now I have 3 times 3x minus 1 plus 4 equals 28. At this point, I would distribute my 3 through the parentheses. So 9x minus 3 plus 4 equals 28. I can combine my negative 3 and positive 4. So I have 9x plus 1 equals 28. Subtract 1 from both sides. 9x equals 27. And divide both sides by 9. So x equals 3. Any questions on that problem? Working with fractions, all of that. All right. Let's turn the page then. Still solving equations, just looking at some applications. So some word problems that would come up where we have to either use an equation or we have to write our own equation. So for this first one, we are given an equation. Scientists have determined that the equation h equals 2.9L plus 78 can be used to approximate the height of an adult on the basis of the length in centimeters of the adult's humerus bone, which is shoulder to elbow. If the humerus is 36 centimeters, how tall is the person? So we're using our formula. H equals 2.9L plus 78. We have the humerus bone is 36 centimeters, so that's going to be plugged into the L. For your application problems, feel free to use a calculator if you would like to, although you are welcome to practice your long multiplication skills because that will come in handy. So we would get 104.4 plus 78. So we would end up with 182.4 centimeters in height. Now this one's a little opposite. So we're told if the height is 168 centimeters, how long is the humerus bone? So I'm going to put 168 in for H and solve for L. Those of you that stepped out of the room, I just said on application problems, feel free to use a calculator if you'd like, or you can practice your long multiplication skills. Subtract 78 from both sides. So we have 90 equals 2.9 L. Then we're going to divide by 2.9. Bless you. And L equals 31 centimeters. I do think I rounded that. I can tell you for sure. Yeah, it was 31.03, so I just rounded that to 31. Questions on using an equation that you are given. All right, next one. A car salesman receives a base salary of $1,200 per month with a commission rate of 5%. If he earned a total of $2,800, what was the value of the cars he sold? Okay, first thing we need to do is try to write an equation that represents the amount of money he makes based on the number of cars or the value of cars he sold. Does anyone have any ideas of what that equation could look like?
If the total is 2,800, then wouldn't that be like after the equals? Like equals 2,800?
Yep, good.
1,200 plus 5x equals 2,800.
Good. So you are right on the right track. I want you to think about something when you're writing equations. So kind of our go-to, and this isn't always the case. We do have a lot of situations where we have like an x plus y equals a number situation. But one of our big go-to equations is the y equals mx plus b equation. And a lot of times you'll see this equation come up in word problems, at least in helping you write them, where b is like a starting amount, and then m is, I usually call it like the amount per, and that could be like per anything, per car, per whatever. And then y is your total. A lot of times you can get far in your equations if you have this in the back of your mind. Like I said, we do run into, when we talk about systems of equations, we have a different setup that we kind of start with. But if we're talking about an equation like this, a lot of times this can get us a long way if you have it in the back of your mind. So I want to take what Caitlin and Elizabeth said and talk about that for a second. So our $1,200 is definitely a starting amount. And then we know we have 5% of whatever's made. The word of in math, well, I don't have a good one in here because it doesn't make sense. But the word of in math always means multiplication. So if I say 5% of the value, that means 5% times the value. Here's the only issue. When you are dealing with percent, you need to turn it back into a decimal. And this is kind of what we're going to be reviewing on Thursday, but does anyone remember off the top of their head how to take 5% and turn it into a decimal? Yeah.
0.05.
How'd you do it?
Well, I don't know. I just remember that like if there's a 0 on the end of it, then that's like if it's 50%, then it's 0.5. So like if it's lower than 10, then you have to have a 0 in front of it.
Okay.
That's my thought process. It's probably not
It's
that
a
close
good
to what I
thought
tried.
process, and it works. Does anyone have a more technical process?
You go 2 decimal places to the left.
Yes. Do you remember why? Yeah. Percent is out of 100. Keep going. Good. Good. So percent is out of 100. What we are actually doing is dividing by 100, which means we are moving the decimal 2 places left. And like I said, we'll review that a little bit more on Thursday, but this would be 0.05. So when you go to write that in your equation, you're going to write 0.05x. And then what Caitlin had said is, well, it equals the total amount he earned is $2,800, so that's on the other side of the equal sign. And that is correct. We are looking for the value of the cars he sold, so the x. So now we're solving an equation. We're going to subtract 1,200 from both sides. So this is going to be 1,600 equals 0.05x. And we're going to divide both sides by 0.05. And when you do that, you get $32,000. Okay, you do want to think logically here. So let's just say we did what Elizabeth had initially said, 5x, right? We get to the end, we divide by 5, so 1,600 divided by 5. You get 320. Would it logically make sense that he sold $320 worth of car sales and he made $2,800? No. So you want to think through things like that. Like if you had written that and you got an answer of 320, you would want to say, okay, something's wrong, and backtrack to what it was. Now we could get to our answer. We'd multiply by 100. Move the decimal twice. Okay. Any questions on anything in that set of notes? That takes care of Thursday's lesson from last week. All right, let's jump then to the first half of today's lesson, so just the 9.2. Oh, your assignment is there at the end for that. If you have the third edition, we can stay after just a couple minutes and make sure those are the same. Okay, next one. Rates, ratios, proportions, and percents. Today, we're going to look at the rates, ratios, and proportions piece. And then Thursday, we'll look at percents. And then next week, we're going to also continue fractions, decimals, percents. And I think I have you scheduled for like a quiz next Thursday. All right, so our definitions. A rate is a comparison of 2 quantities. And I'm going to just make a little clarification. Those quantities have different units. So because of that, we write the units. So this would be like your speed limit, 45 miles per hour. You have a comparison of miles and hours, those 2 quantities, but the units are different. They're not both miles, they're not both hours. So that's a rate. A unit rate means the denominator is 1. So it's per 1 mile, per 1, and you can fill in the blank. We can do this for anything. You will see a lot of rates and unit rates in grocery stores when you're going to buy. And so I always go to like deodorant because that's what I always remember. Like if I go to buy deodorant, I can buy 1 for a certain amount, or I can buy 2 for a certain amount. And I'm like, well, I'm going to eventually need 2. So which one am I paying less for per unit, right? Water bottles, same thing. Like you have a pack of 12 or you have a pack of 8 and they're different prices. Which one is the better deal? So unit rate per unit, so denominator's 1. All right, so you can drive 148 miles on 6 gallons of gas. If we're going to write that rate as a fraction, we have 148 miles over 6 gallons. It's that simple. Notice I do label the units, though, because they are different units. If we are asked to calculate a unit rate, I want this denominator of gallon to be 1. What would I have to divide by to get my denominator to 1? What? 6. Good. You're dividing by the denominator, always. So we're dividing by 6. And again, the rates, unit rate stuff, if you want to use a calculator on, I'm fine with that. So when we do that, we end up with 24.7 miles per 1 gallon. And that would be our unit rate. The first one is our rate. Let's look at number 2. Did you all get that down? Yeah. Okay. You have a salary of $32,240 per year. What is your pay per week, assuming a year has 52 weeks? All right, so first thing we need to do is set up our rate. Our rate is $32,240 per, but we want our unit rate to be in weeks, so we're going to write this with weeks, per 52 weeks. Now we want a unit rate of 1 week. So what are we dividing by? 52. So 32,240 divided by 52 is $620 per week. All right, next one. What is the better buy? An 18-ounce jar of jam at $2.69 or a 28-ounce jar at $3.99? Question, what am I going to make the numerator and what am I going to make the denominator? Elise? The numerator would be the ounces. So why? We got to have a reason. Okay, so I want you to say that again. Say it out loud. Per ounce. Okay, the word per should tell us division. Okay, word per tells us division. If we want to get to per ounce, per 1 ounce, that means that our denominator is going to have to be that 1 ounce. Something per 1 ounce. Okay, so we are going to put our numerator as the money. So $2.69 over 18 ounces. We're going to divide top and bottom by 18. And then here's my other little piece of thing we need to note. Information. When you get this answer, on a calculator it would be like 0.148 something or 0.149. With money, we always round to the hundredths place. But you do need to keep in mind when you're doing some of these comparisons, it is possible to end up with something like 0.149 and 0.147. they would both round to 15 cents, but really the 0.147 is cheaper. So we're always rounding to the hundredths place, except when we make these comparisons, you might have to backtrack to the thousandths place. Okay, so this is going to be 15 cents per 1 ounce for that first unit rate. Then we're going to look at our other one, $3.99 for 28 ounces. We're going to divide by 28. And we will get 14 cents per 1 ounce. Make sure when you're doing these, you actually give me the answer of which one is the better buy. So this one would be our better buy or best option or however you want to label it, but make sure you give me that final answer. Any questions on those? All right. Next example, there are 65 million married women in the USA, of which 35 million are in the labor force. What is the ratio of married working women to married women? Again, this, with the word to, that is setting up your rate. So this is telling us that we should have the working on top, to, meaning over, the married total. Okay, so that's what we're looking at there. So what are we going to set up then for our rate? What number is going on top? 35 million. And on bottom we have 65 million. What happens with all these zeros? Say it louder. They cancel out. Okay, so 1 0 on top of another 0 would cancel out. That's like dividing by 10. And then we can divide by 10 again, and we can divide by 10 again. All these zeros are going to cancel out. Notice that we end up with just 35 over 65. If you have the same, what do I want to call it? The same label, we'll call it label for lack of a better term, million and million, they will cancel out, so you can just use the 35 and 65. Now, if it said something like 65 million and 35,000 or 350,000, you'd probably want to write it out because not all of the zeros on both numbers are going to cancel. But if the labels are the same, million, million, you're really just working with 35 over 65. What are those divisible by? 5. If I divide both top and bottom by 5, I get a ratio or a rate of 7 to 13. We always want to go simplest terms, which would mean fully reduced. And then number 5, a survey said that the average 8th grade student spends 21 hours per week watching TV. What is the ratio of watching TV to total hours in a week? So we want TV to total hours in a week. How would we find out how many hours are in a week? Yep, 24 times 7. So 168 hours in a week. So we're going to do 21 hours over 168 hours. What can these both be divided by?
3.
How do you know?
Because we add 1 plus 6 plus 8, it's 15.
Good. And 2 plus 1 is 3. So both of those can be divided by 3. So let's go ahead and do that. We get 7 over 56. Can we go further? Carson, what can we divide by?
Divide by 7 to get 1/8.
Perfect. So we have a ratio of 1 over 8. All right, so let's just talk for a second then about ratio, because there is a slight difference in these two that we just did versus these first three that we did. Notice on these first three, for our units, they're different, right? Miles to gallon, we have dollars to week, dollars to ounces. When we look at these ones, notice we don't really have units written, because this is 7 married women to 13 married women. This is 1 hour to 8 hours. Now, we can get really specific and say 7 working married women to 13 married women, 1 hour of TV per 8 hours in a week, something like that. But what we end up finding is that we have something we call a ratio. It's like a rate, but it's a comparison of two quantities that have the same units. So we don't take the time to write the units. We can just keep it a fraction, or there are actually 3 ways to write it. We can write it as a fraction, which is what we will mostly do. We can write it with a colon, so 2 to 3. And then we can write it with the actual word 2. 2 to 3. In math, you will most often use the fraction. All right. Last thing for today, proportions. So proportions take 2 rates or 2 ratios, and they set them equal to each other. And the nice property about proportions is that the cross products are equal. So when you multiply on the diagonal, it has to be the same answer. So we can use that to solve proportions. So if we have one fraction equal to another fraction, we're going to cross multiply. So we're going to do 5 times n, which is just 5n. And we're going to set that equal to 8 times 6. It doesn't really matter what side of the equal sign you put these on, as long as you're multiplying the correct terms together. Technically, each of these 4 terms have like a label. I just don't think they matter that much. Like the extreme, it just doesn't matter. So 5n equals 48. Then we're going to divide by 5. And I think your homework will tell you, I think I have it rounding to the hundredths place, but just make sure you read the directions on that and round accordingly if necessary. So this would be 9.6. When we look at our next one, we're going to cross multiply again. So we'll have 5 times x equals 8 times 42. So this will be 5x equals 336. We'll divide both sides by 5. And we get x equals 67.2 for our final answer. Our last 2, we need to set up the proportions. And the important thing to keep in mind when we're setting up a proportion is that your units have to match on top and your units have to match on the bottom. So that's what we're looking for here, is to make sure we set this up accordingly. So if you travel 290 miles on 15 gallons of gas, that's going to make our first rate. It doesn't really matter which one you put on top and bottom as long as you match it on the other one. So 290 miles to 15 gallons. That tells us automatically that miles has to go on the top and gallons on the bottom for our second rate. So then we say, how far should you have traveled on 12 gallons? So our X, our missing number, is on top. And then we can cross multiply. So 15X equals 12 times 290. So that would be 15X equals 3,480. Divide both sides by 15. And we get X equals 232 miles. I do this math in the car. You might not. But if I know like I have to go, I'm going 75 miles per hour, and I know I have to go 150 miles still, how long is it going to take me? And I do my proportions. Maybe that's just a math teacher thing. I don't know. Anyone else? Anyone else? No? Okay. It's just me. Okay. So, and just so you know, what I found is that the difference of like going 70 or 75 or 80, very small difference in time. So it's really not worth going that fast. Okay? All right. When we set up our proportions, remember we need our units on top to match and our units on bottom to match. So we're told that the dose of an antibiotic for a 50-pound child is 2 ounces. Again, doesn't really matter which one you put on top or bottom as long as you match it on your other one. What should be the dose for a 175-pound adult? So our X is going to be with the ounces there. We're going to cross multiply. So 50X equals 175 times 2. 50X equals 350. We'll divide both sides by 50, and we get X equals 7 ounces. Any questions on anything we covered? We covered a ton today. Okay.